Hello and welcome back. This is lecture 2 of Systems 556, 750, Simulating Neurobiological Systems, taught at the University of Waterloo, fall 2021. And I'm Terry Stewart. Now we're going to get into the beginnings of things and start talking about neurons. Okay, so we're going to want to simulate neurobiological systems. At some point, we've really got to simulate neurons. What's that going to look like? What do we mean by that? And as a reminder, I definitely want to make sure that everything we do in this course is pretty agnostic about the level of detail of simulation of the neurons. All right? Because there's quite a range that's out there. Like, you could use a full supercomputer to simulate one neuron in a great amount of detail, or you could simulate a neuron with a single equation. And it's not clear a priori like what way's best. And often what you'll want to do is you'll perhaps want to do something like, oh, okay, well, let's start with a simple model, and then, let's increase the detail when needed. But in order to do that, we've got to get a sense of how in the world we go about simulating neurons. Okay, so what's a neuron? I showed this picture in the last class. This is sort of the canonical generic picture of a neuron. And science knows a heck of a lot about how these things work and how we want to simulate them. One of the core ideas that is pretty consistent out there is the general story of there is some voltage difference between the outside of the cell and the inside of the cell. That voltage builds up, and eventually that voltage hits some sort of threshold, and the neuron emits a spike, produces an output. We got a little bit of a sort of a zoom in over here of like a little close part of this cell wall. What we're actually seeing there is, yes, that sort of story does map onto the actual biology pretty well. There is a voltage difference between the inside of the cell down here and the outside of the cell up here. There are proteins embedded in the cell wall that allow ions of different charged particles to move in and out, and that's going to sort of change the voltage. So that story is sort of standard and correct, but can get into a lot of little details. And in fact, people were simulating neurons well before we knew any of this detail. Okay, so let's start with sort of this simpler sorts of approaches. And some of the really early work trying to figure out how neurons behave is just sort of let's go and observe what they're doing. And what we're going to do is we just have a neuron that's sort of on its own. We're going to inject a little bit of current into it, and we're going to see what it does. Okay. That's what we're plotting over here. I mean, this particular data that I'm showing here is a simulation, but it's pretty close to what would be seen in a real creature. What we're seeing is, all right, we have over time. Now this is just the neuron sitting around doing its normal thing. The voltage difference turns out to be, depends on the neuron, but there's some sort of resting voltage that it's at. We inject some current. The voltage builds up pretty quick. So we're injecting current that's on this axis here. So we're injecting, it looks like 20 picoamps of current. And you can see that the membrane voltage starts going up. And then we stop injecting current, and the memory voltage collapses back down. Okay. And that's sort of, all right, that seems not too bad, fine. Exactly figuring out how to do the math of figuring out why this curve is exactly shaped as it is, that was a lot of interesting research. There's a whole lecture I could give on this particular neuron model, the Hodgkin-Huxley type neuron model that was sort of the first model to really capture a lot of these details. We might talk about that later. We're going to do a slightly simpler neuron model today. But we still want to capture these important behaviors. So, all right, so you inject some current, voltage builds up, and then it collapses back down when we stop injecting current. But what if we want to inject a little bit more current? So all I'm going to do is I'm going to say, instead of injecting 20 picoamps of current, I'm going to go up to 25. And this is the sort of experiments that people were doing early on. And you inject a little bit more current. So all I've done is I'm getting a little bit, 25 picoamps of current. You'll notice the scale on this voltage axis has really, really changed. I mean, we still have the same initial, resting, fine. We're going to inject current, fine. It starts building up. That's the same as this building up here. But now something really different happens. All right? We're only injecting a little bit more current. Something happened here. All of a sudden, the voltage shoots up, drops way the heck back down, and then recovers back to its sort of resting value. Okay. This is a pretty stereotypical behavior. Seems to happen for lots and lots and lots of different neuron models. Exactly how these things are shaped is going to be different for different neurons, but this is what we mean by neurons generate spikes. Okay, there is something really quite obviously weird happening here. And it is these spikes that seem to be the thing that is going to actually communicate signals to the next neuron. So it's these spikes that end up causing neurotransmitter to be released that'll end up influencing the next neuron. That's kind of nice because that means that if we're interested in simulating a full neurobiological system, there's a chance that we can get away with not being all that accurate down here. All right. If it's these spikes that are actually producing a signal that's talking to the next neuron, then as far as the next neuron is concerned, all I really need is to get these spikes right. Okay. Or at least to a first approximation, we got to at least get those spikes right. It's probably likely that if we, want more detail and our that we can probably improve things by also getting the rest of this stuff right. But at the very least, we want to make sure that we get these spike things right. Okay. So, this sort of story, exactly when these details are figured out, sort of the earliest beginnings of this story are Lepeak 1907. This is a while ago, so this is he's playing with frog legs and zapping frog legs and seeing how they respond, and that's sort of where the first beginnings of this particular story that we're going to play here of, hey, look, if we want to model this process, what we can do is we can think of the membrane itself, that difference, that voltage between the inside and the outside of the cell. We can think of that as a capacitor. Okay, that's what a capacitor is in electrical circuits. It's a thing that divides two voltages, and you can inject current on one side and voltage differences build up. But then we also have this aspect that this capacitor is leaky. Okay, when we stop injecting a current, the voltage is going to collapse back down. Okay, that's what we saw here. So we're injecting a current, the voltage builds up. Now a capacitor would not have exactly this shape, but it's going to have something closer to that. Fine. And then this collapsing back down actually looks a lot like exactly the curve that a capacitor would have coming back down. So that we've got those two bits of the story that seem pretty good. Then we're going to have this aspect that as soon as the voltage is going to pass a certain value, that's where we're saying we're going to generate a spike. Okay, that's going to be this sort of idea here of, all right, something weird happened once we got up past a certain voltage, and then so a spike is going to happen. And then for a little bit of time after the spike's been produced, we've got this voltage dropping back down. And it's going to take a little bit of time to recover. And during that time of recovering, even if we injected a huge amount of current, we still wouldn't be able to get that neuron to spike again. Okay. So during this period here, the neuron's like, all right, look, I've spiked. I'm not doing anything else for a little while. Okay. This whole story, putting this whole story together is probably, that doesn't really happen until the 50s or 60s. But the initial parts of the story of, hey, look, we have a capacitor. We can think of it. We've got this leaky aspect, and some sort of, all right, it's got to get up to some value. That's pretty directly traceable back to this 1907 work. Cool. Oh, and I definitely do want to highlight, we know a lot more, again, we know a lot more. There are a lot more detailed models out there. The Hodgkin-Huxley neuron that we may talk about later really does model exactly what is going on here. But we're going to ignore that for now. We're going to take this high-level approximation. Cool. So what does that turn into? That is generally called the leaky integrate and fire circuit. So that's the attempt is to sort of consolidate these ideas together into something that is quantifiable in math. And it's going to end up looking like this. We've got some sort of capacitor. So the inside, we've got the inside of the neuron up here, the outside of the neuron down here. All right. We've got current being injected into the neuron. All right. So this is going to feed current into the neuron. We've got this thing here. This should let current leak out of the neuron. We're being a little bit fancy here and noting that in general, when current is leaking out, it's going to be leaking out towards some particular voltage value. So that's being marked here. So that's just going to be a resistor. Right? So all of this stuff over here, that actually captures pretty well these first two ideas. And is exactly what Lepic was modeling this stuff as. And then, in order to handle this other stuff starts getting to, okay, well, something else is happening. When you hit a certain value, there's going to be a spike, and we're going to just call that there is some reset mechanism. And for this particular model, that reset mechanism, we're not modeling that as any sort of dynamical system or any sort of equations or anything. We're just going to have that happen. Okay. So math-wise, what does that turn into? Well, there's an equation for a capacitor that says that the derivative of the voltage is the current divided by the capacitance. Okay, so all right, a capacitor has some capacitance. That's just a constant. Fine. What's the current? What's the current that's going on here? Well, we've got current being injected in. Fine, that's just this term. And then we've got current that's leaking out. And now, again, we have to use the equation for a resistor. And that's just simply going to be, all right, well, how much current is going across this thing? Well, it's going to be the voltage difference across there times the conductance, and that'll give us the current. So this is sort of circuits 101. That's, the sort of basic circuit diagram should give us that basic equation. Cool. But we've got this caveat. That's what's going to happen when the voltage is less than, when the voltage hasn't, hit its threshold. And then we're going to put in some weird stuff. Now we're going to say, well, all right, if it hits a threshold at some particular time, then we're going to output some spike. And the spike is going to happen at that time. Right? And then for the next some period of time, we're going to force the voltage to the reset value. All right, so that's what's going to go on there. Some weird notation things I'll just point out. This little squiggle delta thing, that is the notation for a thing that is 0 all the time except for at this one instant in time. That's the Dirac delta function. Fine, it just means, yeah, a function that is 0 all the time and then shoots up at that one instant. Cool. Other notation things is sort of maybe reminders of people. It's been a while since people have taken a circuits class. When people talk about resistors, people often either label them with their conductance, how easy it is for things to flow through them, or they'll label them with the resistance, which is 1 over the conductance. That would be a big R, whatever, same things. Anyway, that's what we've got for a basic neuron model. This is sort of this one of the simplest neuron models, and certainly the place where most people start with a spiking neuron model. If you want a neuron model that's going to produce spikes. All right, how good is that model? One way to look at how good that is. So here's a particular thing you might want to try doing. Here we're taking one of those detailed neuron models or an actual physical neuron. Fine. And if let's slowly crank up the amount of current, so that the current that's being injected is being increased over time. Okay. And then we're plotting what the internal voltage is. And yay, we have this voltage. For this first while, we're not injecting enough current. It's not going to spike. Eventually we're injecting enough current, and it's going to spike. It's going to spike. It's going to spike. And notice it starts spiking faster and faster and faster and faster as we increase the current that's going into it. That seems pretty good, right? One caveat I will put in the fact is that with a lot of neuron models and with real physical neurons, if you increase this line far enough, bad things happen and the neuron stops spiking because it just sort of stops being able to work. But within some sort of reasonable range, we should be able to get this sort of behavior. What happens with our leaky integrated fire neuron model? Okay. Pretty similar. Okay, I can sort of increase this current, go run the simulation, I get these spikes. You will notice that the actual behavior of the voltage down here is pretty different. Right, the actual internals of the of what the voltage level is inside the neuron, kind of different. But the overt behavior, the sort of the spikes that are actually going to go cause interaction to other neurons, we're sort of capturing what's supposed to go on there. Okay. Couple other things to note. It's really common when people are doing these leaky integrated fire neurons to sort of, maybe I don't actually care to get these units exactly right. Do I care that the resting voltage is minus 63 or 65 millivolts? Do I care that the input current is in units of picoamps? You can renormalize all these things and keep all of the behavior the same. So it's really common when people are doing leaky integrated fire neurons to say, look, let's just have the resting voltage be 0. Let's have the voltage where the neuron produces a spike be 1. Right? And have it reset back down to 0. Okay, like that. That's just going to simplify my code, and it's not going to change the overt behavior in any way. Okay. It's going to change the scale on this input current. So now this input current is going from 0 to 2, whereas over here it's going from 0 to 60 picoamps, or 0 to, I don't know, maybe 70 or 80. But fine, that's just a scaling factor. I don't care. Okay. Or, sorry, let me rephrase that. I will care if I am wanting to compare it to the actual biology, in which case I just do the conversion. Okay. But when I'm actually simulating it in the computer, I'll just use these sorts of rescaled normalized values. Okay. All right. I can get something that'll do that. How good is that sort of basic leaky integrated fire neuron model? Well, it depends on what you want to do. Here's a picture of a variety of different phenomena that people do find in real biological neurons. Okay. What we're seeing in each of these pictures is at the bottom what sort of input current we're doing, and at the top is the output from the neuron. Okay. So what we're seeing is things like, oh, all right, up here, this one over here, that's actually pretty close to what we're actually seeing, right? That, you know, you've input a current, and yay, spike, 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 it does something. There are other neurons where you input a spike, or input a current, and it spikes once and then stops. There are other neurons where you input a current and it does a little burst and then does nothing, and then does a little burst and then does nothing, and then does a little burst. There's a variety of different things you can find in real physical neurons. The model that I just talked about does a couple of these. So I definitely want to highlight that it's definitely not doing everything. It does a couple of these basic features, and we need to sort of keep that in mind. Of course, one fascinating thing is we have no idea how many of these things are actually used by biology, because most of these pictures, when you take are generated by taking a neuron out of a biological system and feeding in current or adjusting values, and it could be that a biological system just never uses neurons in these sorts of regimes, but there's also quite the chance that it does. So we definitely have to be careful that we have approximated things out, and that's anytime we're going to make a computer model of anything, we're approximating things. My question then is going to be, cool, what can we build out of this simplified component? How close can that get to real behavior? And then I would want to say, okay, cool, if we then add in the details that we simplified out, then we could see, hey, does that detail matter for the particular behavior that we're interested in? That's sort of going to be the long-term research goal. For now, though, we're going to just start mostly focusing on this leaky integrated fire neuron model. Okay. All right. So that's a neuron model that we're going to be spending a fair bit of time with in this course. We should sort of, let's explore it a little bit. Okay. And one way, it's a little difficult to explore it in this sort of differential equation form. Okay. As with this differential equation form, well, I mean, that's great. We're actually seeing when spikes happen and whatnot. We're getting, we could come up with different sorts of inputs and see how that changes. It's going to be hard to explore the space of all possible temporal inputs. So one thing we could do is we could say, well, let's start exploring the domain of, well, what if we just pick an input current and leave it there for a long time and see what its behavior is like? Okay. And then we could pick a different input current and see what its behavior is like at that input current, and pick a different current. Okay. And since the thing that we're interested in, since the thing that affects the next neuron is these spikes, one thing we could then measure is, all right, if I put the input current at some fixed level, how long does it take between spikes? How long does it take for it to spike? How long is it between spikes? Another way to phrase that is, what's the spike rate? So if I hold this input constant for a while, how fast is it going to be spiking? Yeah. So we're going to call this the leaky integrated fire rate approximation. Okay, so it's just going to assume, we're going to assume that the input current is constant. And what we're going to need to compute is, what's the time when the voltage hits the threshold? All right, because we hold the input constant, maybe, there we are. We're holding the input constant for some period of time. That voltage is going to build up. Eventually, it's going to hit this threshold that's going to produce the spike. Okay. That turns out to be computable. Right? we can just analytically, I mean, we could sit there and just simulate it. And just run the simulation, do the, simulate the physics, simulate dynamics, and just see, okay, when does it hit? Here's a situation, though, where we can actually do this analytically. Okay. What we're going to do is we're going to take this equation, okay, and we're basically just going to integrate it. Right? I want to know what, this is how quickly voltage changes, so if I want to know when voltage hits some value, well, that's the integral of this thing. Okay. I've got a little bit of notational things that are going to happen here. One thing I'm going to do is just as a reminder, there's two different ways of writing how a resistor behaves. One of them is to write it as conductance, the other is to write it as 1 over the resistance, whatever, same thing. In this equation, we're going to switch it over to R just because that's a little bit more common. There's also a cool little thing that just tends to come up in electrical circuits all the time, is that when you have a resistance multiplied by capacitance, you get a time constant value. The units of those two things work out to units, that becomes units of seconds. And so it's also really common to collapse those two things down into a time value, because that's actually going to start giving us some sort of intuitions about how quickly the system is going to respond and behave. So those two just identities we're just going to get tossed in here. Other than that, we're just going to take that equation from that previous slide, do those substitutions. We get this thing here. And then we go and ask our nearest mathematician, how do you take the integral of that? Which people either remember or they don't. It's fine. Take the integral of that. We get this thing. Okay. So that's what the voltage will be, assuming that we started at a voltage of 0, and we have a constant input current of J. Okay. Voltage is going to build up. Something will happen. So, but this equation, since we're only using, in order to do that, we were only using this part of the equation, which is only good if the voltage is less than the threshold, right? Because that equation is just sort of ignoring this whole reset mechanism thing. So, fine, all right, but let's actually figure out, so if this is the voltage of threshold, really what we're interested in is what that time is. We know what the threshold is. We know all these things. We want to know what this time is. So now we just do some rearranging. Do some rearranging, do some more rearranging, do some more rearranging, and we get this. Okay, so the time that it's going to hit the threshold is going to be related to this weird time constant thing, which is a property of the resistance to capacitance. So that's just a property of the neuron itself, and and it's fixed. It doesn't change with the input current or anything. And then the log of this term, which is a relationship between, well, the threshold and the input current. If that's how long it takes for it to threshold, and then it produces a spike, and then after it produces a spike, it's going to be in that refractory period for some other period of time, tau refractory. Okay, that means the time between spikes is going to be this plus tau refractory. That's this thing down here. So again, tau refractory, that is after the spike has happened, how long is it going to take for it to recover? Okay. If I want to know what the firing rate is, well, that's just going to be 1 over the time that it takes for it to produce a single spike. So that leads us to this thing over here. Okay. And this is saying, if I put in some current, and I know everything else is just sort of constants, all right? The neuron has some threshold, there's some resistance, there's some membrane time constant, which is the terminology for this combined term that says that is a relationship about the resistor and the capacitance of the membrane. and the refractory period. All of those are fixed. And then as we adjust the input current, this will produce, this will tell us what the firing rate will be. Of course, this is only going to be legit if this tau threshold actually happens. If I put in a small enough current, well, this thing becomes negative. There is no no, it never is going to hit a threshold. That kind of makes sense, right? That is what we saw way back here. I put in a small enough current, it just doesn't hit the threshold. If I put in a little tiny current here, it would just sort of just stay there and not go up high enough for the threshold. So yes, this equation is only going to work in certain ranges. And so we get this. So this is sort of an analytic simplification of this differential equation of this model. Okay. It's only legit for, I'm assuming I'm putting in a constant input current. Okay. But it's going to let us sort of get an initial sense of what's going on with our neuron models. Again, this is going to be a situation where, hey, we can get away with, let's go analyze what happens with the simple neuron model, and then we can add in the more complicated spiking version in the future. I want us to get used to that habit of we're going to simplify things, but we're not going to force ourselves to always simplify things. We can simplify things, see how it behaves, then do a less simple version, see how that behaves, see whether or not that simplification was important or not. Cool. All right. So this leads us to one of the most common rate approximations. So if I'm going to be using a neuron model that doesn't spike, it's not actually producing the spikes. It's just simply saying, all right, I'm going to be, I've got some input current J. That's going to produce an output of, I don't know, 100. And we'll call that 100 spikes per second. So if I have some input current, it's going to do that. Okay. And this is going to be at least one way of coming to terms with, okay, what is that behavior of that neuron? All right, so what am I plotting here on the side? What I'm plotting is exactly what I just said of, well, that full leak, integrate, and fire neuron model, if you kept its current constant at an input of, say, -5, well, it's just not going to spike at all. So its output's going to be 0. I don't have to do any weird, complicated math. I know its output is going to be 0. I feed in no current at all. Yeah, its output's still going to be 0. I feed in 10 units of current. Again, because we went and normalized it, I can't call this 10 amps or picoamps or anything like that. That's normalized input current. So I'm going to put in, so these are unitless, I'm putting in 10 units of current. And it's going to output a value near 250. Okay, so that's going to say that this particular neuron, with a particular membrane time constant and a particular refractory period, is going to, if I was jumping in that much current into it, I would get spikes at about 250 hertz. And we're going to get this nice little curvy thing. Okay. I can put in currents that are kind of low. I can get it lower firing rates. There we are. So this is a very common, this is a leak, integrate, and fire rate mode approximation. And it at least captures some things. Like it's biologically motivated. The parameters have biological meaning. Like I can go ahead and say, all right, I can go ask a neuron, hey, there's particular neurons in a particular part of the brain. What are the values of these two things? All right, so these parameters of my neuron model have things that match onto biology. So that's great. It captures some of that interesting behavior. So the fact that as you increase the current, the firing rate does not go off to infinity. It starts flattening out. And that's something you definitely see in biological systems. Great. So it captures that. It's faster to go and compute things. So we're going to be simulating these things. Right? So it's faster to go and compute this than it is to actually say, okay, here's the differential equation, run it for a second, run it for some period of time holding the input constant and go and compute that differential equation over and over and over again and find out how many times it spikes. That would be very slow. So this is pretty faster than that. It's not the fastest neuron model. If you're going to go ahead and ignore spikes completely, you can come up with a faster equation to compute than this. We'll see some in a moment. But this still isn't too bad. It does have some other concerns. One interesting thing is that if I'm injecting a current that's kind of low here, like just below threshold, this thing just says, okay, look, no, I don't spike, I don't spike, I don't spike. In a real biological system, there's enough sort of random noise and fluctuation that if you inject a little current down here, it doesn't have this really sharp onset. In a real biological system, you'll get some spikes if you're injecting a small amount of current down here. Okay. So that's also a thing that, all right, that's not quite as nice as biology. It's not quite matching what a biological system would do. But we have things where we can inject some sort of current, we can get a number out, and it's not too different from what the biology says. All right. There are those two parameters, and these are parameters that do vary in biological systems. The sort of normal range, somewhat typical in biology, is this membrane time constant. So this is sort of a measure of how quickly current will leak out. Is something on the order of 20 milliseconds. That tends to be about the biological range. That's what we'll be using as a default. The refractory period, how long it takes for the neuron to recover after spiking, generally something around 2 milliseconds. And as you vary these things, the curve that you get out definitely changes. If current leaks out over longer time, you get a much more linear increase. And if your refractory period, of course, is much larger, well, one way you can think of it is the refractory period, sets a limit on how fast it can spike. If the refractory period is 20 milliseconds, then there's no way this neuron can fire faster than 50 hertz. Right? If it takes 20 milliseconds for it to recover, it can't fire more than 50 times in 1 second. So you're going to see much more sort of this direct saturation effect happens pretty quickly. This is probably well out of the range. I don't know of any neurons that go up that high, so that's sort of a little bit extreme. But what we're indicating there is, yes, these particular curves can definitely be affected by these parameters. And the nice thing is these are things where you can actually go and look at real biological neurons and say, okay, what sort of values do we have? Cool. All right. So that's going to be a common approximation that we're going to use. I do want to spend some time talking about some of the other approximations that are kind of out there. The most common neural approximation now, and the thing that is used in all big, giant, deep neural network sort of simulation things, is what's called the rectified linear unit now. This is the most blindingly simple neuron model. That's this, right? It's just this function. It's just a maximum function. It's just the output is the same as the input unless it would go negative, in which case set it to 0. Right? This is ridiculously fast to evaluate. Has some really nice properties if you're doing backpropagation learning. So there's all sorts of reasons that people use it in big giant neural networks, sort of the traditional image processing and face recognition sorts of algorithms. As far as its comparison to biological systems, it's not horrible. Like, it doesn't capture this sort of saturation. All right, but fine, it does something. It doesn't do that smooth onset thing. Fine, whatever. It's not as bad as one might see, or It's not a horrible approximation. Okay. But it is definitely ignoring some things. Do those things matter? Well, that's, again, I'll highlight that as we're getting up to building larger neurobiological systems, we can go and explore exactly that question. We can say, okay, well, let's build them using these. Let's build them using these. What's different about the behavior? Okay. Does it matter? So, all right, that's a nice simplified one. There's also some other variations, so you can do a smooth really. All right, and that's got exactly, that starts getting this smooth spike onset. Okay, again, still doesn't saturate. A little bit harder to compute. What else we got? Another really common one, or sorry, this one used to be common. So in the 80s and 90s, when people were doing neural networks, this is what pretty much everyone used, and now it's been taken over by the rectified linear unit. Sometimes it was called the sigmoid neuron. Technically, sigmoid just means any curve of this shape. The particular shape that everyone used was the logistic function, which is this math here. It's got this nice smooth onset. It's got this nice smooth saturation sort of thing. So it's also sort of, you can say things about how it sort of maps somewhat onto the biology. A little harder to actually, make it fit a particular neuron model because it doesn't have the particular parameters that we're looking at with the leak integrated fire. What else we got in here? Oh, I guess there's also the hyperbolic tangent, which also used to be a pretty common one. That one's one weird fact about that is, oh, well, all the models I've shown so far, the output is always positive. If we're just treating the output as math, okay, the output could be negative. What does that mean? At that point, we really can't think of this as a rate anymore. We're starting to be really abstract. We're starting to get away from the biological system. It starts being much harder to map things that we're doing here onto what the biology is saying. Okay, but they're also out there. Okay, so that's a bunch of different ways that we would want to think about what it means to model a neuron. I will definitely stress that we can go way more complicated than this. So let me go all the way back here. I mean, we started with sort of like the simplest versions. This differential equation thing that was sort of our, okay, this is going to be our leaking rate and fire equivalent circuit. There's a lot more we could do there. And when I say that people sometimes use full supercomputers to simulate a single neuron, that's because they are literally doing, all right, let's have thousands of these differential equations. And we can get closer and closer. We can definitely add way more detail and way more accuracy. And that's something we'll want to be able to do. We don't want to start with all of that complexity. So where we're generally going to be starting in this course for the next couple lectures is we're going to stick with this approximation. And then we're going to step back up to actually doing the full differential equation, because we really do want to model what's happening over time. Right. So that's going to be the plan for the next couple chunk of this course. We're going to start with, fine, we have these neurons, what can we do with them? How can we get these neurons to actually do useful work? And then we're going to go up to how do we take this same neuron, but a spiking version of it, to do work. All right, and that's our plan for the next little while. There we go. So that is like this lecture on neurons out of the way. Next, we're going to get up to how can I make these things do things. Thanks, and we'll see you then.